Today, we will be presenting our science fair project about electrified solutions made by Kiera Arthurton, Andrew Romero, and Janine Owen. As we all know, fossil fuels play a major role in the rapid increase of climate change. The negative impacts have led to multiple global disasters such as wildfires, extreme weather, and high sea levels. Nevertheless, numerous methods were reviewed when confronting this problem. Exploring electrochemical reactions can lead to a more efficient way of splitting water molecules, resulting in the production of hydrogen gas. This clean energy source offers alternatives to harmful fossil fuels and can be used in various applications such as fuel cells, energy storage, heating, and cogeneration. The goal of this project was to find a connection between pH and electric current by applying two separate voltages to two identical water salt solutions. The resulting ion production, caused by hydrogen atoms drifting from the oxygen atoms in the water, may cause a change in pH. The significance of this experiment was to split water molecules, creating oxygen and hydrogen gas, and use the hydrogen gas as a fuel for energy. Observing how separate voltages affect sources of water can test the effectiveness of electrolysis as an alternative source of hydrogen gas. By generating hydrogen gas, we can broaden our possibilities and lessen our reliance on non-renewable sources of energy such as fossil fuels. Our question: does electricity affect pH? Our hypothesis: if an electric current is passed through a salt bridge via salt solutions, then the pH of these solutions will change. Additionally, this is expected that different voltages applied to the solutions could lead to a variety of results occurring in the pH levels or in general. For this experiment, our variables were voltage in batteries and types of water. The independent variables. Our dependent variables were the pH level distilled in tap water and also the magnesium sulfate solution. The control variable was the 200 milliliters of water.
One of the key components in finishing this project was the materials used for the experiment. To prepare the solution, we required paper towels, scissors, water, Epsom salt, small pencils, plastic spoons, measuring cups, and a pH meter. The batteries were set up using wires, snap connectors, wire strippers, alligator clips, and various voltage types. For the procedure, we filled 2 cups with 200 milliliters of water, then weighing about 45 grams of Epsom salt on a scale. Using a plastic spoon, we thoroughly mixed it when added to the water. After that, we transferred 75 milliliters of the solution to 2 different small cups, as well as checking the starting pH of the solution with the pH meter. Nextly, we put a small pencil in each cup and used 2 paper towels, each cut into 7 centimeters, placing 1 paper towel in each of the 2 solutions, establishing a salt bridge. For the batteries, we connected the 10V to the 9V snap connector, attaching alligator clamps to the wire, reacting to the pencil's graphite. Then cutting 2 pieces of wire, 30 centimeters long, and removing the insulation from the wire's end by roughly 4 centimeters, securing the stripped wire to the 20V battery and the pencil's graphite with alligator clips. In order to determine whether there would be a pH difference, we chose to conduct 5 trial runs with the identical voltage levels for each individual solution, the solutions being salt water, distilled water, and tap water. Every 20 minutes, we would check to see if the pH had changed from the initial pH, making salt water become the solution with more variation of results. You can see that the pH of distilled water would likewise shift at the end of each hour, although not as much. Last but not least, the pH difference for tap water would actually end up bringing less difference in results compared to distilled and salt water solutions. The data from the experiments is visually summarized in the bar graph, allowing us to compare the variations between the 10V and 20V batteries in order to examine how the reactions affected the experiments differently for the salt water, distilled water, and tap water. Based on the comparison chart, it indicates a considerable variation in the voltage results, as we can conclude that 20V would be a more efficient voltage for reducing pH, serving as a more practical supply of hydrogen.
Our results concluded that, when using the 20V battery, the water had a fast reaction and bubbles formed as a result of the graphite pencil. A rise in pH was also seen. The 10V battery resulted in a lower pH every 20 minutes, prompting the formation of bubbles to be slow in comparison to the 20V battery. The results showed tap water gave little to no reaction, distilled water showed a slight difference, and the saltwater solution displayed the most change in pH. The main conclusions we reached were the following. 1. Electricity is effectively able to change the pH of water. The 10V battery would increase the pH, while the 20V will result in a decline. 2. During the beginning of the experiment, bubbles will start forming intensely while using the 20V, even burning off some of the graphite of the pencil. The 10V solution will start forming bubbles, but at a slower pace than the 20V. The bubbles are a result of the drifting hydrogen atoms. 3. The water displayed different results, which leads us to believe that the outcome is due to the differences in voltages. Recommendations that we would suggest are 1. Using different voltages to see how it would have changed the pH. 2. Adjusting the amount of magnesium sulfate to see how it affects the pH. 3. Using one voltage and apply it to a multitude of solutions to observe differences in pH. And 4. For more detailed results, measure every 10 minutes. Finally, our bibliography displays the many sources we used for this experiment.